Let's look at two possible formulations of the Fourier series on top of what we have just seen. The first formulation is the one that we have built from the eigenfunctions. We have found the eigenfunctions sine k and x and cosine k and x with kn equals to n pi over L. And I'm going to claim that this is the same thing as having an infinite sum from minus infinity to plus infinity of Cn times the exponential of the imaginary number times Kn times x. So we use the Euler formula. We write e at the I theta as cos theta plus I sin theta. So we can write cos Kn x as 1 over 2 e at the I Kn x plus e at the minus I Kn x. And the sign is very similar, except that it's 1 over 2i, and now we're taking the difference between the two exponentials. So with this application of the Euler formula to writing as complex exponentials, the sine and the cosine, we plug these complex exponentials back in the definition of the Fourier series that we have seen before. Then we have f of x being a0 plus a sum that goes from 1 to infinity of 1 over 2an plus 1 over 2i bn, all of it times e at the I kn x plus e at the minus I kn x multiplied by 1/2 an minus 1 over 2i bn. We call one of the two c at the c minus n and the other cn. You might notice that they are complex conjugate. an and bn are real. That means that the imaginary part between cn and c minus n has switched sign. So we can write f of x as the infinite sum from minus infinity to plus infinity of cn exponential of minus I kn x, where we define for negative n's k minus n equals to minus kn. Then we have c0 is equal to a0, and cn is a combination of 1/2 an and 1 over 2i bn with a negative sign for positive n's and for a positive sign for negative n's. As we do for an and bn's, we can also write cn as an inner product. So cn is also equal to 1 over 2l integral from minus l to l of fx e at the power minus I kn x. This is the same structure of inner product as we did for computing an and bn, and you can in the same way retrieve the previous definition that we gave of cn as a combo of an and bn. So we have two possible interpretations of a Fourier series. Either we can say that cos kn and sine kn are two eigenfunctions associated to the same eigenvalue lambda n, where lambda n is always positive and n ranges in the natural numbers. And we also have to take care of the fact that there is this constant eigenfunction that is just the constant 1. Or we can think of e at the I kn x being the only complex eigenfunction associated with lambda n, where now n takes any integer value, and lambda n can also be negative if n is negative. Actually, lambda is negative when n is negative, so it can be negative. And this translates properly in the sense that if we do the inner product of e at the I kn x times f of x, then we have a product between exponential of I kn x times a infinite sum of cn times e, I, k, and x. Then we can take out the infinite sum. We have a product. This product can be written as, inner product can be written as an integral. This integral is 0 unless kn plus km is equal to 0. And this is satisfied only if n is equal to minus m. So we do retrieve the same thing times a coefficient because we hadn't rescaled the eigenfunctions. So this makes sense. As an overview, we can either look at Fourier series with trigonometric functions that has the pro that we only have positive indices, so our sums goes from 1 to infinity. Everything is real, but we have two series to take care of, the sine Fourier and the cosine Fourier, and the odd constant eigenfunction. Or we can look at complex exponentials that has the pros of only having one series without any exception, but the constant is complex and you have to take care of it.